our today's episode, we will learn about elimination reactions. An elimination reaction is one that involves the loss of two atoms or groups of atoms from the same or adjacent atoms of a substance, leading to the formation of a multiple bond. Multiple bonds may be double or triple bond, depending upon the relative positions of the atoms or groups eliminated. These reactions are classified as alpha, beta and gamma elimination reactions. Children, let us now learn about types of elimination reactions. We will first learn about alpha elimination reactions. In these reactions, the loss of two atoms or groups occurs from the same atom of the substrate molecule.
Children, let us take an example. Let us try to understand base-catalyzed dehydrohalogenation of chloroform to form dichlorocarbene. You see on the screen a base reacting with chloroform to form dichlorocarbene, water and chloride ions. Children, do you know dichlorocarbene is the reactive intermediate involved in carbylamine reaction and Rearrangement reaction. Let us now learn about beta elimination reactions. In these reactions, the loss of two atoms or groups occurs from the adjacent atoms of the substrate molecule. For example, acid-catalyzed dehydration of alcohols and base-catalyzed dehydrohalogenation of alkyl halides. Let us have a look at the acid-catalyzed dehydration of alcohols. You see on the screen that alpha and beta are the two adjacent carbon atoms in ethanol. Now, in presence of catalyst sulfuric acid, dehydration of alcohol takes place to form ethene and water. Let us learn similar case of base-catalyzed dehydrohalogenation of alkyl halides. When ethyl bromide reacts with a base, that is potassium hydroxide, in alcoholic medium and the reaction mixture is heated, ethene is formed along with potassium bromide and water. Children, let us now learn about gamma elimination. In these reactions, the loss of two atoms or groups occurs from alpha and gamma positions. Now children, where are these positions? You can see that they are three bonds away of the molecule, leading to the formation of three-membered rings. Let us take an example. When 1,3-dibromopropane reacts with zinc dust, we get cyclopropane along with zinc bromide by the process of gamma elimination. This reaction is called Freund reaction and is extensively used for the synthesis of three-membered rings.
Children, let us now learn about mechanism of these reactions. Two types of mechanisms are proposed for these reactions: the E1 mechanism, the E2 mechanism.
Hughes and Ingold proposed E2 mechanism for the elimination reaction that proceeds by second-order kinetics. This reaction involves a single step. This means that the base pulls a proton away from the carbon atom and simultaneously a halide ion departs. This elimination results in the formation of double bond. This also means that the halogen takes its electron pair with it. Hydrogen leaves its electron pair behind to form the double bond. These are the electronic changes that happen during dehydrohalogenation. In the transition state, which you are seeing on the screen, two bonds the CH bond and the CX bond are being broken simultaneously. Now children, tell me, where does the energy for this bond breaking come from? It comes from formation of the bond between the proton and the base and from the formation of the pi bond between the carbon atoms. The rate determining step is the only step which involves reaction between a molecule of alkyl halide and a molecule of base, and its rate is proportional to the concentration of both the reactants. Have a look at the reaction on the screen, which shows that rate is proportional to a constant K multiplied by concentration of alkyl halide multiplied by concentration of base. This mechanism was named E2, that is elimination bimolecular. What does the word bimolecular mean? This means that the reaction involves two reacting species.
Children, let us now learn about evidences for the E2 mechanism. We will first learn about kinetics and absence of rearrangements. Children, do you know what is the evidence for the E2 mechanism? The elimination reactions that follow second order kinetics and are not accompanied by rearrangements. The rate determining step, which is the only step, involves reaction between a molecule of alkyl halide and a molecule of base. This results in second order kinetics. Children, let us now learn about isotope effects. These second order eliminations show a large hydrogen isotope effect. Different isotopes are atoms of same element having different masses, and because of this, their chemical properties are not identical. The same chemical reactions can occur, but at somewhat different rates. A difference in rate or position of equilibrium due to a difference in the isotope present in the reaction system is called an isotope effect. For example, a bond to protium represented as H is broken faster than a bond to deuterium represented as D. For reactions of this kind, in which hydrogen is abstracted as an atom, positive ion or negative ion, the observed reaction rate is 5 to 8 times faster for ordinary hydrogen as for deuterium.
Children, let us consider the dehydrohalogenation of 2-phenyl ethyl bromide represented as C6H5CH2CH2Br. 2-phenyl ethyl bromide reacts with sodium ethioxide in the presence of ethanol to form phenyl ethylene. As you see on the screen, formation of carbon ions from 2-phenyl ethyl bromide would involve conversion of the base, that is, the ethioxide ion, into its conjugate acid, that is ethanol, which is also the solvent. Now children, what happened in the actual experiment was that the substrate was ordinary, that is unlabeled 2-phenyl ethyl bromide, and the solvent was labeled ethanol, that is C2H5OD. Consider what would happen if carbon ions were formed reversibly. This means that most of them would regain hydrogen to regenerate starting material before eventually losing halide ion to yield the alkene. But nearly all the molecules of solvent are C2H5OD, not C2H5 OH, and so, in the reversal, the carbon ion would be almost certain to gain a deuteron, not a proton.
Children, let us now have a look at the element effect. Second order eliminations show a large element effect. It has been pointed out by Joseph Burnett that evidence on this point has existed for many years in what he has named the element effect. Heterolytic bond dissociation energies show that the strength of carbon halogen bonds follow the sequence shown on the screen, which shows that carbon halogen bonds for alkyl fluorides are the strongest. Can you tell me the reason why? This is due to small size of fluorine atom which attracts the alkyl group more strongly than the iodide ion, with the rate of reaction reflecting the ease of breaking the carbon halogen bond. The differences in rate are quite large. For example, alkyl bromides react 25 to 50 times as fast as the corresponding alkyl chlorides. Thus, for the elimination reactions, the reactivity of alkyl halides follows the sequence shown on the screen, which means that reactivity of alkyl iodide is more than alkyl bromide, which in turn is more than alkyl chloride, making alkyl fluorides the least reactive in the series. And with element effects of just about the same size, alkyl bromides react 40 to 60 times as fast as the chlorides. And to take the full range of reactivity, alkyl iodides react more than 25,000 times as fast as the fluorides. Clearly, the rate of breaking the carbon halogen bond does not affect the overall rate of elimination. Children, thus only the E2 mechanism fits all the facts and is generally accepted as the principal pathway followed by 1,2 elimination. Let us now learn about the E2 reaction orientation and reactivity. So far, we were concerned with the evidence that second order dehydrohalogenation proceeds by the E2 mechanism. Now, let us look at some other characteristics of this reaction. Dehydrohalogenation, as we have seen, often yields a mixture of isomeric alkenes. Children, can you tell me, in such a case, which isomer, if any, will predominate, which will predict the orientation of elimination on the basis of molecular structure?
From alkyl halides or haloalkanes. Alkyl halides on heating with a strong base such as sodium ethoxide or a concentrated alcoholic solution of potassium hydroxide undergo dehydrohalogenation to give alkenes. The halide ion may be a chloride, bromide, or an iodide. This process of removal of a molecule of a halogen halide such as hydrochloric acid, hydrogen bromide, or hydrogen iodide from a haloalkane to form an alkene is called dehydrohalogenation. Children, dehydrohalogenation is an example of an elimination reaction, since in this reaction a hydrogen is removed from a beta carbon and halogen from the alpha carbon. Therefore, it is called beta elimination reaction. Let us take an example. When iodoethane, that is ethyl iodide, reacts with alcoholic potassium hydroxide at 353 to 363 Kelvin, ethene is formed along with potassium iodide and water. Similarly, when 1 bromopropane, that is N-propyl bromide, is reacted with alcoholic potassium iodide at 353 to 363 Kelvin, propene, potassium bromide, and water are formed. The ease of dehydrohalogenation of alkyl halides having the same alkyl group but different halogens is iodides are more reactive than bromides, which are more reactive than chlorides, while for isomeric alkyl halides having the same halogen but different structures is tertiary is more reactive than secondary, which is more reactive than primary. Thus, a tertiary alkyl iodide is most reactive. Children, let us now learn about Sedzev's rule, which states that an E2 reaction will preferentially form the most stable alkene isomer. Alkene stability generally increases with branching at the alkene carbons. In reactions of removal of hydrogen halides from alkyl halides or the removal of water from alcohols, the hydrogen which is lost will come from the more highly branched beta carbon. Sedzev's rule implies that base-induced E2 eliminations will lead predominantly to the alkenes in which the double bond is more substituted. Have a look at the position of the double bond. The use of sterically hindered bases raises the activation energy barrier for the pathway to the product predicted by Sedzev's rule. Thus, a sterically hindered base will preferentially react with the least hindered protons and the product distribution will be controlled by kinetics and will result in Hofmann's product. Children, do you know what is a Hofmann's rule? In bimolecular elimination reactions, in the presence of either a bulky leaving group or a bulky base, the hydrogen that is lost will come from the least highly branched beta carbon. Have a look at the formula on the screen. You can see that hydrogen will be lost from less branched beta carbon atom and the product formed will be as shown on screen. Children, let us now discuss an example on Sedzev's rule. Depending upon the structure, alkyl halides may give one or more isomeric alkenes. For example, dehydrohalogenation of 1-chlorobutane gives only one alkene, that is but1-ene, since only one type of beta hydrogen is available on the left side of the molecule. If, however, the structure of alkyl halide is such that it has a beta hydrogen on either side of the carbon atom carrying the halogen, it can undergo elimination in two different ways, giving two alkenes. The relative amounts of these two alkenes is governed by Sedzev's rule. According to this rule, whenever two alkenes are theoretically possible during a dehydrohalogenation reaction, it is always the more highly substituted alkene, that is, the alkene having lesser number of hydrogen atoms on the double bond which predominates. For example, when 2-bromobutane is treated with alcoholic potassium hydroxide and heated, more highly substituted alkene, that is more stable alkene, but2-ene is obtained as 80% yield. But1-ene is the less substituted alkene which is obtained as 20% yield. The alkene with greater number of alkyl groups is the preferred product during dehydrohalogenation of alkyl halide as it is formed faster than the other alkene. So children, the second product is formed according to the Hofmann's elimination rule, which is the opposite of Seitzeff's rule. In certain elimination reactions, the less substituted alkene is preferred. Example, when base is bulky, like tertiary butoxide. The formation of the less substituted alkene in an elimination reaction is called a Hofmann elimination, and product formed is Hofmann product, whereas when more substituted alkene is formed, it is called Seitzeff's elimination, and product formed is Seitzeff product. If bases are large, that is bulkier, due to steric hindrance, less substituted alkenes are preferred. That is, Hofmann's product will be formed. But if base is small, more substituted alkenes are preferred. That is, Seitzeff's product will be formed. In a compound which can eliminate to give different alkenes, the more highly substituted alkene is the major product. This generalization is known as Seitzeff's rule. Exceptions to this rule occur in two circumstances. First, when the proton to be removed is in sterically more environment. The use of a base whose basic center is also sterically hindered can lead to the predominance of the less substituted alkene.
Children, let us now learn about the second mechanism, that is the E1 mechanism. For the reaction proceeding by first order kinetics, Hughes and Ingold propose the E1 mechanism. In this mechanism, the electronic changes, that is the bond breaking and bond making, are the same as in E2 mechanism. Here, however, they are taking place not simultaneously but one after the other. Where E2 involves a single step, E1 involves two steps. In step 1, the substrate undergoes slow heterolysis to form halide ion and carbocation. In step 2, the carbocation rapidly loses a proton to the base and forms the alkenes.
We recognize step 1, that is, rate determining step, is identical to the first step in SN1 mechanism. In step 2 of E1, the carbocation reacts with the base to yield the elimination product. Children, a carbocation may combine with a nucleophile, rearrange to a more stable cation, eliminate a proton to form an alkene. This mechanism was named E1, that is, elimination unimolecular.
Children, let us now learn about evidence for the E1 mechanism. What, in your opinion, is the evidence for the E1 mechanism? The elimination reactions that follow first order kinetics are not accompanied by a primary hydrogen isotope effect, show the same effect of structure on reactivity as SN1 reactions do, and where the structure permits are accompanied by rearrangement. Let us examine each one by one. First order reactions primary hydrogen isotope effect ਨਾਲ ਜੁੜੇ ਨਹੀਂ ਹੁੰਦੇ ਹਨ। ਇਸ ਤਰ੍ਹਾਂ ਦੇ isotope effect ਉਹਨਾਂ elimination reactions ਵਿੱਚ expect ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ ਜਿਨ੍ਹਾਂ ਵਿੱਚ beta carbon hydrogen bond rate determining step ਵਿੱਚ ਟੁੱਟਦਾ ਹੈ। It is expected in E2 with its single step, and a large primary isotope effect is in fact observed in second order eliminations. ਇਸ ਨੂੰ E1 ਵਿੱਚ expect ਨਹੀਂ ਕੀਤਾ ਜਾ ਸਕਦਾ जिथे second step which proton lost हो जांदा है. Children, we will now discuss about reactivity in E1. In E1, as in SN1 reactions, reactivity is determined by the rate of formation of the carbocation, and this we have seen depends upon the stability of the carbocation. Where the structure permits, these first order eliminations are accompanied by rearrangement. Again, we turn to the fact that the first step is the same as in SN1. Since this first step yields carbocation, it follows that E1 should be susceptible to rearrangements and of exactly the same kind as those characteristics of SN1.
Children, let us now learn about rearrangement during dehydration of alcohols. During dehydration of alcohols, sometimes unexpected or rearranged alkenes are formed. This is due to the reason that carbocations are the intermediates. If the initially formed carbocation is less stable, it rearranges either by 1,2-hydride or 1,2-methyl shift to form the more stable carbocation, which eventually loses a proton to form the unexpected or the rearranged alkene. Let us take an example. Dehydration of 1-butanol or 2-butanol with concentrated sulfuric acid gives the same mixture of 1-butene and 2-butene, in which the more highly substituted alkene, that is but-2-ene, predominates. This is in accordance with Sidzeff rule. The formation of this mixture from 1-butanol can be explained by rearrangement of the initially formed less stable 1-degree carbocation to the more stable 2-degree carbocation by 1,2-hydride shift, which then loses a proton in accordance with Sidzeff rule to afford a mixture of but-2-ene, which is formed as the major product, and but-1-ene formed as the minor product. 2-butanol under these conditions gives directly the more stable 2-degree carbocation, which then loses a proton to give the same mixture of 80% 2-butene and 20% 1-butene. Similarly, when 3,3-dimethyl butane 2-ol is subjected to dehydration with concentrated sulfuric acid, the initially formed 2-degree carbocation rearranges to the more stable 3-degree carbocation by 1,2-methyl shift, which subsequently loses a proton to yield 2,3-dimethyl but-2-ene as the major product in accordance with Sidzeff's rule.
Children, let us now learn about the orientation of E1 reaction.
Elimination by E1 shows strong Sidzeff orientation. That is to say, when more than one alkene can be formed, the more highly branched, the more stable alkene is the preferred product. Thus, a di-substituted alkene is preferred over a mono-substituted, and a tri-substituted alkene is preferred over a di-substituted. Orientation and reactivity are still determined by relative rates of reaction, but of different steps. How fast the substrate reacts is determined by the rate of step 1, but which alkene is produced is clearly determined by which beta proton is lost faster from the carbocation in step 2. The 2-pentyl cation can lose either a proton from C3 or form C1 to form 2-pentene or 1-pentene respectively. There is a competition and more 2-pentene is obtained because 2-pentene is more substituted.
Today we have learned about elimination reactions, in which we learnt about E2 and E1 mechanism. So, I hope that you all have enjoyed today's lesson. See you next time.